good morning. Thank you for all of you for showing up again. It's 2015. It's another year of our workshops. This is the first in a series of 4 that we're going to have this year. We'll try to have them again every 3 months, and we're really appreciative of your continued support for these events. In case you have any ideas of what the workshop should be about, what the topics of interest to you, please contact either one of us in white shirts, Enbridge shirts, or Maria directly, or send an email to your ESC with the topics of interest, and we will try to accommodate them as best as we can. Before we go into this workshop's topic, I just have a couple of questions for everybody. Did everybody have a chance to fill in the energy management questionnaire in your welcome package? That would be greatly appreciated if you could. That's one. The other one is, we're also playing with an idea for our next workshop to be situated at one of the sites of our customers. So if any one of you is willing to help us out and be sort of like a host site that we can then use some of the ideas that we implemented at your site as a topic of a workshop, we would of course financially support that. But we think there is a great value of you guys actually seeing some of these implemented measures in place. So if there is anybody interested in hosting that kind of event, please let us know, again, any one of us, or drop us an email, or contact Maria at the exit. That would be greatly appreciated as well. So on to our today's topic at hand. What we're going to talk about today is energy management. But energy management not in a high-level topic as we used to do last year. We feel that after 12 months of our work, people are pretty comfortable now with having some sort of data in their facility. So we have some meters installed. We're getting the data. We have our production numbers. The goal of this workshop is to start looking at what to do now with the data. Some of you have already gone down the road of having that, but many people have not. Many people are not quite sure what to do with the mass of data that they have. So we'll try to explain how to start at least. And then in the future workshops, we might explain what the next steps. But without these basic steps, you will go down the road with energy management, and you could potentially end up in a very wrong spot. So we're trying to avoid that. Also, this is not a very interactive topic. We try to develop some of the workshop, like work examples that we can all work through, but it's not very well suited for this. You need a laptop, you need a computer, so we will try to accommodate as best as we can. At one point, we will also have a real-life demo that will be led by George and Slobodanka. They have laptops, they will run these regression analysis. If you have any questions, we would encourage you to just split up and talk to individual people, and if you have questions, they can show right on the laptop. So I think that's much better than going through the manual regression analysis, which would be very painful. So let's start. You've seen this commercial for our programs before. Most of you, this is not your first visit with us. But for those who haven't, we're really trying to accomplish a very high-level goal of energy efficiency for our customers. I'm not trying to get you to use less or more gas, or less or more electricity, or less or more water. I'm trying to get you to use the resources as efficiently as possible. That's our goal. So whatever we can do to help you with that, we will do that. And how we do this is very familiar to all of you in manufacturing facilities, continuous improvement circle. We develop the knowledge, workshops like this. Our energy solutions portal, for those of you who don't know, you can log in. You have very simple calculators there. We're working now on 4 or 5 extra calculators. That's going to be feed water economizer, condensing economizer, reduced exhaust in the facility. So that will all be coming up in the next 3 or 4 months. So I would encourage you to visit that. It's login is free, and once you log in, you can check your opportunities. You can do all sorts of nifty stuff with energy efficiency, and you don't have to call on anybody. You don't have to deal with anybody. Once you do have results from that, because it's such a generic calculator, we would encourage you to call your ESC and say, look, this is what I got. Does this make sense? Opportunity identification, speaking of making sense, we don't expect to be the main drivers all the time of our ideas. You work in your facilities, you probably have gazillions of ideas coming from everywhere. What we're trying to be is sort of like a little funnel, a little sift, to see which one of these ideas make sense, which don't, and at a fairly detailed level, to save you time and money. That's what we're trying to achieve with our program. So opportunity identification, we can be there for you at no charge to you to go through these ideas with you. Measurement, as we talked about, we participated in financial incentives for a lot of meters for your facilities so far. We continue to do that. We encourage this because we think the more data you actually get, the better your projects are going to get, the more energy efficient we'll all become. Because there is nothing like seeing the data and seeing the ways that we create every day. Engineering analysis as well. All of our ESCs, energy solution consultants, are engineers. All of them have experience in manufacturing facilities before, so they're a great resource to you guys, if for nothing else, to bounce ideas off of. And then action and implementation. This is the part where, unfortunately, it's all up to you. We cannot do that for you. We can provide financial incentives for implemented projects, and we do. But ultimately, action implementation is for you. So all our groundwork is there. So when you go and ask for funding from your facilities for some energy efficiency measure, that we are sure that we gave you all the information to be as accurate and realistic as possible. Because we all know that if you go and ask for $100,000 and you tell somebody they're going to get back $100,000, getting back $99,000 is not good enough. Right? So we're trying to really cover you for that. We speak from experience as well. Again, we saved huge amounts of energy so far to our customers. 110 million cubic meters of natural gas, 20 million kilowatt hours of electricity, 800,000 cubic meters of water in 3-year period alone. So this is significant amount of energy. And of course, for the customers, you get not only cost reduction, you get reduced CO2 emissions, and you improve your bottom line. So we feel that this program is a win-win for everybody. There's always room for improvement. So if you have any ideas, any questions, if you think that there is something that we can help you with, do not hesitate to tell either one of us, your ESC, send an email to us. Be vocal. Tell us what you want from us. That helps us be better. Okay, so after this brief commercial, question, why manage energy in the first place? It's all nice to have energy management, but why would you do that? What are the benefits, right? So everybody thinks energy benefit is directly because energy management, energy benefits. Lower energy consumption, reduced emissions. Knowing when energy is used helps you. If you do contracting for energy, you know how much you have to buy. What your profile of usages helps you get a better pricing. You can make better capital investment decisions. Do you really need a new oven, or can you do with the oven that you have? Do you need a new boiler? And of course, accurately allocate costs. I had a couple of customers who are selling the energy to each other. Accurately accounting for that cost is crucial. So those are all benefits of managing energy that are energy specific. Right? But there is also non-energy benefits that very few people connect. So operational improvements, set points. Many people have had heat exchangers, huge heat exchangers. I had a customer who had a heat exchanger, then when it went down, it cost them $250,000 to clean it. So they wanted to be absolutely sure that that cleaning is necessary at that time. Not before, not after. So getting energy management in place that actually told them how much energy is being recovered in that heat exchanger solved that problem for them. They didn't have to guess. They could wait until the energy recovered on the other side is a certain percentage. That triggered the preventive maintenance. That helped a huge deal. That was energy management. Better preventative maintenance, increased uptime, and more capacity. Of course, if you don't have to do unscheduled downtime, you will create more capacity for yourself with the existing capital equipment. Of course, improved quality as a result of better uptime, more capacity. You have more time to focus on the things that matter. It will result in the improved quality. Again, result of the energy management. All of it leading to tighter cost control. Because we understand that even though we talk energy, you guys are measured on your costs, on the quality and cost of your output. So all of that actually serves tighter cost control. So if a good energy management conserves energy, reduces emissions, and saves money everywhere in the organization, then the supporting energy management structure, the processes in place, should provide means to control how the energy is consumed. It should be embedded into every aspect of the organization. It makes energy visible. This is a very big topic for us. I'm very passionate personally about this, making energy visible, because I feel that if somebody sees every day what it costs them to run something, they will actually act on it. Energy is raw material. Energy can be affected. Energy can be managed. It is not a given that you have to pay a certain amount of dollars every single month. You can control that. That's a huge, huge point. So how do we see this structure? We call it Comprehensive Energy Management Program, and the way we see it is we start with the senior management sponsorship. Again, huge step, because when we talk energy management and we want to put energy management into every aspect of the organization, we need senior management support to actually spread the word to everybody and to hold everybody accountable. Right underneath that, energy team consolidation. Energy team consolidation, we'll talk about it a little bit later, how it is, but don't think of it in the strict terms of, I'm going to create positions just for energy teams. That's not what this is meant. Long-term energy reduction goals, if you have no goals, you will probably never reach them. Simple as that. And then continuous improvement. Again, something that we use every day on every other aspect of our lives, but somehow energy managed to escape so far. We want to put it back into there. So importance of senior management sponsorship. I went to the few sites myself, and I know my ESCs deal with this all the time, and they say, well, I have a great support from my VP of whatever the flavor of the month is. And it's like, I got my support, I can go and implement energy management. We just had a case, very big customer, VP of engineering, huge, huge, huge favorite or fan of energy management. They went about 80% into their energy management process. They had it almost implemented. The guy retired. Guess what happened to the energy management program since? He died. Right? It's not only good enough to have one member of the senior management. You want to have as many as possible, because that will ensure sustainability. When that one person leaves or gets focus changed or whatever it is, you will have somebody else to back it. So this cannot be a pet project. This cannot be a project where just one guy does it or lady does it because they're just interested in energy management. This has to be embedded into the culture of the organization. And I know that's a huge task. That's a given. So reason why is because this, even though, when the senior management gets together for their meetings and they talk about their kids and their hockey tournaments and all that stuff, they also touch about other subjects, such as corporate financials, corporate strategy, and the risks to the corporation. These are guys that are very busy. These are boardrooms that are full of ideas how to accomplish those three main goals. So if we can show them energy management in light of those three goals, you will do yourself a great favor. Don't talk in energy management just as a green initiative. Talk about a cost allocation initiative. Talk about cost reduction initiative. Those are the things that they want to hear. Your risk is lower if you manage your energy. Your financials get better, and your strategy can be then that you're greening your environment and you're greening your production process. So all of those can be wrapped up in a nice tight bows, but we have to understand what they talk about. Like as an example, if this is their world, energy management is probably this line, this dot over here. Very, very low on their radar. We have to make sure to move it from there, somewhere there. That's our goal. So the first business case that we should be making to the management is for the energy management structure itself. Processes in place that will stay past either our teams or current VP sponsor of the year. These processes have to be embedded into your organization. So how are you going to do that? Of course, you need to provide the costs and benefits upfront to the management. If they understand that, they have something to fight for. They have something to grab onto and say, oh, I get it. I'm going to save $100,000 if I do this. Even better, I'm not going to be exposed to $200,000 potential for some sort of energy up cost that might happen 3 months from now. That's what you want to do with energy management. It helps you to get that buy-in. So costs and benefits analysis, just like any other business case. Energy is no different than any other business case you've ever done. On the cost side, you have financial investment and you have human resources investment. It takes your time, it takes time of your colleagues, it takes time of somebody else who's going to track all of this. But on the benefit side, risk mitigation, strategic benefit, and financial benefit. All of those need to be defined and provided to management in the simple to understand terms. Costs involved, I will not talk too much about it. Last time when we had energy management workshop, we talked about some of the upfront costs and hardware and software costs. They're relatively easy to ascertain because you ask the people that you want to work with for quotes. You know what your time is worth it. It's not easy, but it's straightforward to assess. The problem is with the benefits. How do you define the benefits of the energy management structure? It's not something you buy. It's not something that you get a warranty that says you will get 3% or 17% or 38%. You have to get a feel for it, and unfortunately, this feel depends on each one of your facilities. There is no one formula. So you need a little bit more of a complex assessment for that. You need what we would like to call a facility energy audit. And that's a very important step because it will tell you where your energy is being used. Without knowing where it's used, you cannot ascertain what the savings potential is. One thing that I always want to stress is facility team must be involved. It's always tempting to give this to the third party, hands-off approach, but that does not work. It's good to have third party who is an expert in the field to lead it perhaps, but facilities team has to be involved because once the third party leaves, it's all on you. So you want to know what that was. So what does it encompass, such an audit? First, you have to define the boundary. What do you want to actually manage to start with? If you're a large automotive supplier, you probably don't want to have all of your plants doing energy management all at once. You may want to focus on 1 or 2 facilities. Or if you have a very complex facility, then maybe you want to focus on 1 or 2 processes that are major energy users to start with. To get sort of like our feet wet, to get a feel for how this works. Second thing that you will have to define is what is your so-called base period, and we'll talk about it a little bit later. Then you have to observe current energy consumption within that boundary and over that base period. You have to understand how much energy has actually been used there. And third one is identify and prioritize expected energy drivers. So when you go out there and you say, this is the boundary that I'm working with, this is the energy that's being used here, what is driving this energy? Which button moves the energy needle? Because if it doesn't, you don't want to put it in this audit. If it does, you want to understand how much, where, and who's the owner of that button. That is very important as part of the energy audit. And this is a second question that we get very often. Is this really necessary? I mean, I read that energy management saves you X% of your energy, and this is my business case. I don't need a facilities audit to do that. It is true that it's not mandatory. You do not need it. But these are some of the things that you have to consider. And the list is not all-inclusive, but I thought these are the most important things. So you have example savings range from anywhere from 2 to 15%. How comfortable you are to go to the management and say, I'm going to save 15% if the potential range starts at 2%? What are the downsides for you saying to management you're going to save 15%? On the other side, if you say, well, I'm going to go conservative, I'm going to say 2%, there may not be a business case to do that. So you want to know where you're at in that range. And the only place to start with is energy audit. Are you after cost savings or actual energy reduction? Those are two different things. They can track each other, but they don't have to. You can just beat us up or beat your supplier for the energy cost. You get your energy cost down, you're done for the year. You haven't spent one less cubic meters, but you saved cost. So if that's your goal, then probably energy audit is not all that important. But if you're down to the reduction of actual energy consumed, energy audit becomes very important. How active are you already? I know some of you guys here are already well down the energy efficiency path. If you are down there, you already know where your energy is going. So you probably don't need it. Some of you are starting from scratch. You probably will need something. So it does depend on your situation. Unfortunately, there is no one pill that solves all our problems, but it's within your control. You can affect it. Energy team is the second most important thing. You did your business case, you explained costs and benefits. Energy senior management team was like, yep, okay, we want this. Let's start the energy team. So effective energy team has to have more than one person. It's not a team if there is only one person on it. I know that lots of us have been put in the position where we only have ourselves in that team, but that's not a team. And it won't result in the savings you're hoping for. Do form a cross-functional, not cross-fictional team. Those are two different things. We want people from all sorts of, all areas of organization, but we want them to actually participate. We want people who pay our bills, and we want the people who are down on the shop floor who's tinkering with the set points actually consumes energy. We want all of those viewpoints on our team. Include subject matter experts if you can. Whether that's a third party, whether that's one of our ESCs, whether that's one of you, you have to have some subject matter expert. I was on an energy team at one of our facilities, one of our customers' facilities. They didn't even know what BTU is. Maybe they need to find somebody who knows what BTU is. It's all good to know accounting, but you need to know both sides. That's why we have teams. That's why we don't have to know everything ourselves. And have that management sponsor that you got attend these meetings, at least on an occasional basis. It shows people that that matters. Leverage expertise of all those team members. So if you invited them, they're from all corners of your organization, use that knowledge. Some of the best practices for energy team, set expectations, first and foremost. What will energy team accomplish? What are the goals? Why are we putting together a team? Write energy team charter. Long-term energy reduction goals. What are we going to accomplish as a team? By when? Who's going to do what? Establish required time commitment. Don't think that these people will just do all of their regular daily jobs, or 3 or 4 of them, and then come to these meetings and be effective. You have to allocate some of the costs and some of the time for the people to actually focus on this. It's difficult in our environment, I realize that, but it needs to be done. Lastly, empower team to actually make changes. If somebody has a good idea, go on the shop floor, change things. See what happens. Because if all is going to be just academic and discussion, again, that will not save energy. Actions save energy, not talk. Talk's cheap. And lastly, energy team's goal is to make energy visible for everybody by putting them on reports. We don't have that today, but imagine 5, 10 years from now, the world where you go on to production meetings in the morning that says, last night we were done 22 minutes, we produced 22,000 widgets, and we spent 10,000 kilowatt hours doing it. And this has been our best kilowatt hour per widget in the last 3 weeks. That's how you're going to get the energy visible. That's how you're going to make changes. If the energy is visible only to 2 people in the corner that nobody actually even knows exist, energy will not be of any use to anybody else in the facility. If you look at this, for those of you who are familiar with either lean manufacturing or Kaizen principles, this is essentially a Kaizen principle. This is a Kaizen event. Put energy team together, go down on the floor, assess your process, find what's wrong with it, fix it, get on with life. That's what energy team should be. Energy team should not be on an entity on its own forever and ever and ever. It should resolve a problem, move on to the next problem. So if our facility is complex and we want to energy manage only one line, resolve that line, fix it, move on to the next line. That's how you get things done. That's how you move energy ahead. And yes, I realize for me it's easy to talk, it's harder to implement, but we have to start somewhere. So setting reduction goals, again, one of those topics that's highly contentious. How do you get it? You hear all these people benchmark it, set your goals based on the best practices in the industry. Do I go to do that? Do I do it against my historical performance? What do I do? Everybody's a little bit confused with this, where to start. Again, it depends on your particular situation. If you've been doing energy management for the last 10 years and you're very good on energy efficiency, maybe it's time to look at the best practices in the field. But if this is your first kick at the can, and this is the first time you want to implement energy management, I highly, highly recommend using your best historical as your first target. Because otherwise you will set your target so high, people will get immediately demotivated. However you set them, targets have to be smart. This comes from HR, straight from HR, but it's true. Specific, measurable, achievable, realistic, time-bound. Specific, so it's nice to say I'm going to reduce a lot of my energy. Well, what's a lot? It's much better to say I'm going to reduce it by X% or by so many gigajoules. Not by a lot, not by a little. Measurable. There's a lot of people who will then set the values to some odd combination of the KPIs that people down on the floor who actually influence energy use cannot affect. Then what you will get is total confusion, because they will not know what they affect, and they will not know how their action actually affects that big, giant KPI you have at the end of the line. So it has to be something that is measured parameter, that they can see, turn the button, the needle moves one or the other way. Very important. They have to be achievable. Don't set unrealistic targets. If somebody tells you, I'm going to make you improve your production by 300% over the next 6 months, you will probably sit back and say, okay, let's see that one. But if somebody says, let's go and reach 103%, maybe it'll be better. At least you'll have a fighting chance. If you don't give people a fighting chance, you will demotivate them instantaneously. This is a point that we already went through, but it's important to repeat. Best practices are good. They're aspirational goals, however, because you do not know exactly how the best practices goals have been achieved. When you read any one of the articles, even ours, when you read that and says, we achieved this, it doesn't tell you all the little bits and pieces. And we all know the devil is in the details. So you want to know how those guys achieve best practices before you set best practices as your goal. So you can have it as aspirational goal, but you cannot have it as your operational tactical goal day in, day out for the operations. And they have to be time-bound. Again, yes, we want to reduce it by 10 gigajoules, but if we want to reduce it by 10 gigajoules by the end of 2020, by the end of 2050, or by the end of this year, it's important. How much effort is going to go into it? Depends on how fast and how much you want to reduce. Any questions or comments on this part so far? Excellent. Next step, assessing the baseline. We talked about it as an energy audit part. What is our baseline, right? So somebody smarter than me said this, every journey starts with a single step, and it's very true. You have to start somewhere. No matter how complex your project, recall any one of your complex projects you participated in. You might have had 300 different steps on your MS project chart, but it had to start at the beginning, at the first milestone. Same with this. You have to start somewhere. So successful energy management implementations have always started with a fact-finding mission to define what is our base case, what is our as-is today case. Because if I would tell you, I want you to reduce something by 10 gigajoules, I have to know that you're already using about 90 gigajoules. Because if you're using 1 gigajoule, you will have a hell of a time getting 10 gigajoules out of the system. You need to understand where you're at. So if you haven't had the facility audit process, now you have to do these steps again. Define the boundary. What are you going to use as your boundary? What are you going to use as your base period? Observe the current energy consumption and identify energy drivers. So whether you do it in a facility energy audit step or here, it's irrelevant, but it has to be done. In addition to that, when you're doing the baseline, now there's 2 extra steps. You have to now check if those expected energy drivers actually affect the energy. So you have to generate the baseline energy model, and then you have to check whether that model makes sense. And why is that? Because to develop a baseline, it takes a certain amount of time. Right? So you have to go either back into history to get the time, or you have to start now and wait 6 months until the baseline is done. At the end of that process, regardless how you look at it, you will use your baseline on a go-forward basis. So you don't want to be 6 months yet ahead and say, ooh, now these numbers don't make any sense anymore because I forgot something. So that's a very important step. Accurate baseline is required. So this is where our ESCs, if you need some help, we're happy to help you. To be there to say, do these numbers make sense? Why do they make sense? Why do they not make sense? Again, free help. So let's start with the defining of the boundary. First step, what are we going to do? Whole facility. If we have a relatively simple facility, then we can use a whole facility as our first step. You have a meter data at the entrance of your facility, be it natural gas, electricity, whatever it is, and you have only maximum 1 or 2 energy drivers. So weather-dependent consumption may be one simple line that only makes one product in one particular fashion day in, day out. That you can take whole facility and you won't go much wrong. But if you have complex sites, if you have multiple energy users all over the place, you want to look at the major energy users first. And then what I call limited scope and limited investment energy management. Start there. Identify something really important, draw a boundary around it, energy manage that part. It can be a boiler room, it can be a major paint line, it can be a major oven, whatever that is, start there. So this is just an example, right? If you have steam boiler that uses 90% of your consumption and you have little 2-unit heaters, you have facility meter, you can probably get away from doing the energy analysis based on this meter, and you don't need a heck of a lot of other stuff. So that's a facility-wide candidate. But now if you have 22-unit heaters, 4 different size makeup air units, 2 paint lines that are completely different and they operate differently, now it's your decision. Do you have enough resources to handle all of that at once? Because regression on this meter will be a hell of a lot more complex than the last one. Or do you want to split it up and focus on, say, this line or the steam boiler or makeup air units to start with? You have to make that decision early in the process. It will affect how much energy you spend. It will affect the results. I personally like to start small because then I can show some gains. Management starts to believe in our results, and then we can go on to more serious things. But it's your decision to make. We will support you any which way you go. Once you define that boundary, now you have to go into base period. And I keep going about the base period. Why is it important? It can be weeks or months. If your energy analysis shows that you're using pretty much the same amount of energy day in, day out, and your production levels are pretty much the same, you can probably do like 6 weeks worth of analysis and you will define your energy base case. You're good to go. But if your load is largely seasonal, then you will probably want to look at least 1 year worth of data to see the impact of the changes. Because you want to go through the base period that encompasses entire range of your energy drivers, maximums and minimums. For statistical analysis to be valid, you have to work with the data that encompasses the entire range. You cannot say, I'm going to only work from 10 degrees to 15 degrees Celsius for my base case, and I'm going to analyze minus 20 degrees Celsius weather. That has serious statistical implications. So you want to make sure that your energy driver encompasses a full range of extremes. Regardless how you get there, this point of data collection interval I cannot stress enough. Have all data sources report at the same interval. Most of you will say, who would do it differently? Again, speaking from experience, one customer had implemented a very expensive system, energy management system, that reported the kilowatt hours in every 15-minute intervals. Of course, not in the full 15 minutes. It was something like 8 or 9 and then 15 minutes further and so forth. Natural gas was reported at 8:05 and then every 15 minutes. Their production was reported in the shifts. It took us months of work to actually get data cleaned up enough to be useful. So don't do that. Get them at the same interval. And considering that you usually work in some sort of constrained space, what data you have available, monthly data is acceptable, but it's minimum acceptable interval. The closer the data, the more often the data collection happens, the better off you are. The more statistically valid analysis becomes. Coarser data collection, of course, requires longer baseline. So if all you have is monthly data, you will need a longer baseline. You cannot do statistical analysis on sample of 3. Again, lesson learned, do it based on the production reporting. Energy management is usually secondary implementation after you already produce something in your facility. So your production people already have cadence of when they want results. They already have cadence of reporting. Use the same cadence for your energy management. So if all you have the data for is shift-based, use energy management in shift-based. If it's hourly, use an hourly data. You don't have to go much more than that. Third step is now understanding the energy consumption. You have the base period, you have the boundary that you want to work with. What's your energy consumption there? So we have a little example. You have it in your workbook as well. So let's say we monitor one line within the larger facility. Let's say we make one widget every minute, operate 16 hours a day, 5 days a week. It's fairly simple. And it's within GTA, so monthly temperatures for 2013 and 2014 listed there are averages for GTA area. So this is what the numbers look like. So if you look at the report, it's fairly straightforward. I chose monthly report just to make this example very simple to follow. These principles that we're going to describe here are applicable for any number of samples, for any time frames. I just chose this as an example here because it's easy to follow, and if I put more than 12 rows, you probably wouldn't be able to see it as well. So that's why we did it. So you can see there time when I took that, outdoor weather for that month, production output for that month, and the consumption that we actually metered for that particular line. So that was on the submeter. First thing first, every time I'm a visual person, every time I deal with data, I want to plot it out. What does it look like? So when we did that, in green you have natural gas consumed, in blue you have a line of the outdoor temperature, and in red you have the production output. So immediately when you look at this data, it tells you a few things. It tells you that yes, you have some seasonality in your data. There's some peaks and valleys as the temperature drops. But it's not very significant. You're still stuck with about 180,000 cubic meters per month of usage regardless of the weather. So that's typically your base load, your process load. And you can tell that the production is fairly flat because you make one widget every minute, 16 hours a day. There's not a heck of a lot of changes.
Does that line change if the weather is volatile?
No, that's production output. Right? No, this is gas consumed here. That changes. That's a good question. So the second one that I want to do is scatter plot. I plot consumption, again, of blue dots are consumption versus the outdoor temperature. What that tells me when I look at the data, there's very little variation in the usage. It goes from 200 to 250,000 for very cold weather. And I'm pretty much bound down there by, 185,000 cubic meters per month or thereabouts. So I can tell that my base load is very high. And if I'm going to focus on anything in this energy management process, I'm going to focus on my process load. Because yes, I can save some on the seasonal load, but it's not going to be significant. So I'm going to focus on the process load. So that's how you should look at the data. Right? And then we have just a summary of that, how you look at the data. Look whether you have seasonality, how much base load you have, do you have the production steady or does the production change? All of that plays effect. Second, so now that we know what our energy looks like, we understand what influences it roughly, let's really identify these energy drivers. So we already have the two. Outdoor weather, we said, it changes a little bit. Production load changes it significantly. So what are the other ones? Now it's time to go back to the Kaizen principles. For those of you who have been part of it and in manufacturing, walk the process. Go down on the shop floor and say, on this process, for this particular line, I'm going to walk down there, I'm going to talk to the process operators, I'm going to talk to the engineers who designed the process. I'm going to say, what affects this process's energy consumption? What is it that the person on the shop floor actually changes? And when they change that, how does that reflect it in our energy consumption? That's how you find the energy drivers. Some people refer to energy mapping. There's gazillions of different names for this. But you essentially walk the process and collect the data on how the energy is being used and controlled. Goal of it, identify any and all operation variability that affects the energy use. Any and all of it. So we have the data, we have the consumption, now we know what the energy drivers are, now we have to connect the two. We have to say, these are the energy drivers, this is the energy, how are they connected? And we use a mathematical model for that. So essentially we take weather, production, any other drivers that we found, we put it in the big black box, outcomes predicted energy consumption, everybody's happy forever and ever. That's the basic steps. In this particular case, we call something called regression model. Most of you are familiar with it. But it answers the basic question, what's the relationship between the variables? And the way they do that, it relates one numerical dependent variable, which is usually called Y variable, or what is that we're trying to predict, and one or more numerical or categorical independent variables. Those are usually X variables. And those are the ones that we say, what explains or influences our Y variable. It's used mainly for prediction and estimation, which is exactly what we want to do here. We want to predict what our energy use will be based on the inputs. And this is what the formula looks like down on the bottom. Predicted natural gas use is some sort of A is an intercept or constant, which explains what our consumption would be if all our explanatory variables are 0. Then B is a slope. It's a rate of change that particular factor contributes, and each one of these factors has one of the B's. So it goes B1 all the way to Bn, n being the number of variables. So in this particular case, predicted natural gas is some sort of constant plus outdoor weather times B1 plus production output times B2. All the science behind the regression analysis can be summed up in this formula. But before we actually use the model, we have to remember some basic things about the models. Again, somebody smarter than me said this. Don't always trust the statistics without actually using sanity check, because you will be wrong. Statistics is no better than the computer program. Garbage in, garbage out. Quality information in, pretty good information out. So we have to be very careful of that. There is no substitute for common sense. There is no mathematical formula that will save us from using our common sense. So when you get a formula out of any sort of system you use, look at it and say, does that make sense? So if you see, for example, the formula for the outdoor weather, and if your consumption indicates increased consumption with the lower temperatures, chances are your model is not good. Unless you have really good reason why that would happen, the model is not right. So don't trust the model blindly. I got that from the internet. You can go on the tylerwigan.com. The guy actually has a bunch of these examples. US spending on science, space, and technology in green versus suicides by hanging, strangulation, and suffocation in red. What do they have in common? Nothing. Correlation is 0.992. Your R squared will be 0.99. It's a perfect model. Meaningless, but perfect. Common sense. So, bad news, good news here, of course. Bad news is you and your team are the only ones, the best judges, to judge if the model is right or wrong. No consultant, no ESC, not any one of us from the outside know the process as well as you do. So use your knowledge. Check that. We can help you with the model building, we can help you with the data collection, we can help you with lots of things. But you have to look at the model and say, no, that makes no sense at all. And then we go back and redo it. Right? Good news is that understanding of these basic engineering principles solves all your problems. It's very simple to adjust and iterate the model once you know that the model could be wrong and once you know what affects it. So it's still within your control. All of you are more than capable to find that. So don't be afraid of the models, but use them to your advantage. We are here as well. If you need second set of eyes, if you need to bounce the ideas off of, if you say, have you ever seen anything like that? We're here to help. Ultimately, it is you who knows your process the best. So going back to our examples, we put that nice little formula in. We got our linear regression. We have consumed natural gas, and we're going to put it into the model, knowing the limitations of the model. How do we do that? Lots of people think this is some very complex software, very complex science. You can make it complex. There's very nice packages out there on the marketplace, very complex. They range from $10,000 to $270,000 that I worked with, and I'm sure that the range is higher for others. But you can start with as simple as Excel tool. It's built into your Excel. It's called data pack analysis software. I'm going to quickly show you how it's done, and then George We'll show you live demo on the laptop, and Slobodanka there has a laptop as well. So if you feel like you want to ask more questions, we'll have about 10-minute break after this. You can take a look at the demo, you can ask questions, and then we'll reassemble and go forward, okay? So to start with, you find the Data tab on your Excel tool. You press Data Analysis button over there. There's a pop-up that says Data Analysis. You scroll down, you find the Regression tool, and you click OK. Then this comes up. Input Y range, input X range. Y range is your natural gas consumption. Your X range is all the other variables. You want to make sure you have line fit plots, so it gives you a nice little graph showing you how your regression fits the data. And you press the button. That's it. For the start, you can use your simple Excel tool. So your energy team, they meet together, they assess all the information they have, they put it into simple Excel tool, they do presentation like this for themselves and say, does this make sense or not? That's as simple as the start of your energy management journey. George, please take over. We'll just switch the laptops here for a second. After this, there will be a 10-minute break. Oh.
When you're using production output, are you using actual dock widgets, or are you using system in widgets? System in being, this is what we tried to do, so much went to the dumpster, so much went to the dock.
In this particular example, there's only one line, so I'm using only that line input, but that's a very good question.
Does that include waste or not include waste?
That's a very good question. It should include your waste. It should never be, there's lots of people who will do, let's say this is a paint line, and it'll put some damage to the paint, they'll put it again through it. You cannot not count those, or you don't want to count them double. You want to be able to count in what in that hour went through the line, whether it's successful or not.
So only if it goes through the process being measured.
Correct. There is no room for work in progress here. George, can you start?
Okay, so here's our data. We have a data stamp here. We have a column for natural gas consumed. This is that 7-year data that Damir was referring to. We've also pulled some weather data from Canada, and then we've also recorded what our production output is. This is what the model is predicting after we do the regression, which we'll go through. And simple as that. So that linear regression line of best fit that Damir had mentioned is in this output. So the R² value is 0.95, which Damir will talk about exactly what these mean. But just to define the line, your y-intercept is this value here. Your slope times the variable of outdoor weather is this value. Your slope times your production value is that value there. So it's as simple as that. Does anybody have any questions regarding using the data pack in Excel?
I remember Steve Dixon showed this similarly before, but I think there was a relevance. The E numbers or the F numbers. If they're not below a certain threshold, then that particular coefficient is variable.
Exactly. So there's significance to each variable, and what Damir was talking about before is not every independent variable will define your dependent variable, and that's in this analysis here. So you can see your p-value is the probability. So what's the probability of these dependent or these independent variables actually having an effect on the model? So this is the probability that these variables actually make a difference, or it's by chance.
So closer to zero, the more certain.
Exactly. So the smaller this p-value is, the less probable that this model came together by chance. So there's
I just want to throw it out there that
we will go through that in future slides, right?
yeah, it does have a bullshit sniffer built into it, is what I'm saying.
Correct. And we will actually have slides on those bullshit snippets.
Okay.
So if there's no questions, we'll have a little break. So the output of the analysis that George and Sloba did is listed right here. It is also on your workbook example. It's called baseline period. For those who can't read it right on the screen, it's a lot of information on the screen, but it's right on the baseline period. Underneath the formula, there is an output. So that's the output what it looks like when it comes out of the Excel. There is nothing to it. But there's quite a bit of information on this output. So we'll go now through all of these factors that people have been asking about and try to explain what they actually mean. Any questions are welcomed. So first thing that we're going to look at is what George explained is these coefficients. Those are the actual coefficients that go into our regression formula. We all know what the regression formula is. So we'll make this a little bit bigger. So I took these coefficients, put it there. So intercept is 18,000 and something, outdoor weather is minus 2,000 and something, production output is 11. So when you look at it, how are we going to translate that into our actual usable formula from the generic regression formula? This intercept is essentially your A factor. Coefficient is 18,040, so you put into your formula 18,014 instead of the coefficient. B1 is the factor that affects the outdoor weather. It says outdoor weather, the coefficients minus 2,000. You put it into the formula next to as a multiplier for your outdoor temperature. And the leftover is the B2, which is production output. Coefficient is 11. And you put it into coefficient next to the production. So that's how you arrive at the generic regression formula you can now use. So what are we going to do with that now? We're going to take the formula, we're going to put outdoor weather and production output in the formula above for each month. So once we do that and calculate predicted value, this is what we're going to end up with. We get the column with the predicted natural gas usage. Each one of the values is calculated using the regression formula for its particular outdoor weather production output for that month or for that time period. Yes?
Temperatures there then would be as I asked you, if you're right, the Environment Canada
Correct, for the month.
Okay.
If you're doing the monthly. If you're doing,
Nothing to do with degree days at all.
this has nothing to do with the degree days. The reason I don't use degree days personally is because degree days have come from the residential sector. Degree days are usually referring to the temperatures above 18 degrees Celsius, usually, not always. And then that introduces, I don't know how many of you in the facility actually get to 18 degrees Celsius in your heating. Your setting might be 21 degrees Celsius, but your internal heat load, the gain that you get from all your equipment, actually turns off your heaters probably somewhere around 12 degrees Celsius, maybe lower. I know facilities where they go down to 7 degrees Celsius, and they have enough internal heat gain. So if you use 18 degrees as your heating degree day and use heating degree days, you will build in some error in your formula. That's why I don't use it personally. Same with the cooling degree days. Did that answer your question? So everybody's now, oh, this is easy. I thought this was complex. This is really easy. Everybody's like, I don't understand what the big deal is. Is it correct, though? That reminds me of that joke that we used to have in the production in my old days when we said the guy is going to be paid a little bit of money for all the knowledge, but he will be paid for a lot of money for knowing exactly where that knowledge is applied. This is the same thing. Is it correct? Anybody can do the mechanics of it, but is this model now working for us? How do we know that? First thing to check is, what do our residuals look like? George has made a point to talk about them already. We'll go over them again because they're important. So residuals are essentially, you take consumed actual gas in that period, you subtract the predicted gas for that period, and you get what is called a residual. It's a fancy statistical word for leftovers. So those are the leftover values when you take what's actually being consumed minus what your model predicts. And you get random values there that are only useful once you put them into some sort of graph. And the graph for our particular values look this way. On the x-axis is predicted value. On the y-axis is the residual amount. What you want to see is tight and uniform in number residuals around the zero line. What that tells you, is that your residuals, your essentially guesses of the model to your actual consumption, are equally distributed on the plus as they are on the negative side. If all the residuals are hanging on the top, it means that your model is constantly under-predicting. If they're on the negative side, it's over-predicting. So something's wrong with your model. It has to be roughly even on both sides. They have to be tight around the zero line. That's the best residuals you're going to get. So that's a very quick check to see whether the model makes sense to begin with. Not the only check, though. The other parameters that are important for this is something called adjusted R-squared, standard error, F-statistics, p-value, and intercept. So let's start with one at a time. In green, highlighted are all those parameters and where you can actually find them. Again, this is a little odd to read on so many numbers on one screen, so I apologize for that, but I think you can find the areas at least. You have R-squared here, adjusted R-squared, standard error. Here are the coefficients we already talked about, F-statistics, and p-values for each individual factor. These are the actual values from the chart, so you can see what we're talking about. R-squared, 0.958. Adjusted R-squared, 0.949. F-statistics, 102. P-values go from 0.66 down to practically 0. Constant and intercept is 18,043. So what are these parameters? Adjusted R-squared is coefficient of determination. Essentially, it tells you what is the proportion of variation in your natural gas prediction that can be explained by your model. So what are the energy drivers that you put in? How much of that model are they actually explaining? That's what R-squared is telling you. Every time you add variable, your R-squared becomes better and better and better. So if you put 15 variables, your R-square will be pretty close to 0.9999999. And since you want it to be between 0 and 1, you would think it's a great model. The problem is R-square itself will always grow. Every time you add variable, it will grow, even if you add meaningless variable. That's why you have to look at adjusted R-square. For multivariable regression, you always want to look at adjusted R-square. Standard error essentially tells you, if the standard error is large, it tells you that your model is not all that reliable because it's not sure whether it's correct or not. It just gives you a lot of window for errors. So you want standard error to be as tight as possible. F statistics essentially tells you whether the independent variables taken as a whole do explain the dependent variable. So whether all those 2 or 3 variables that we have, whether they explain your predicted gas usage. The higher the number, the better off you are. There is no magic threshold, but the higher the number, the better off you are. So if you do 2 or 3 models and you want to compare them, the higher that F statistics go, the better off the model you have. P-value is another one important one. It's a confidence level. It essentially tells you what is the probability that I'm wrong when I think that I have statistically valid model. P-value usually you want to be below or equal to 0.05. And if you look at this as a percentage, it will be 5%. An easy way to remember p-value is if you want your confidence level to be 95%, your p-value has to be 5% or less. If you want confidence value of 90%, p-value has to be 0.1 or less. So whatever is left over from your confidence to the 100%, expressed in decimals, that's your p-value. You do p-value for each individual variable. 1 p-value for intercept, 1 p-value for the outdoor temperature, 1 p-value for the production levels. So you can look at it the other way around. If you have a model, you get an output, your p-value is, say, 3. You can dump that variable out of your model because it's statistically insignificant. And then you can rerun the model with less variables. It's always better to run with more variables and thin them down rather than the other way around. Intercept itself. High intercept relative to your original point can be indicative of something you missed. Means that model, let's say in our case 18,000 out of 180,000, 10% of the load is still not explicable by all the variables we put in. The model is saying, this 10%, I'm just going to keep it. Always is there, but I don't know why. So the higher that intercept, the less chances you have that all your energy drivers are accounted for. There could be exceptions to that, but that's a general rule. So why is it important to get that right? Because once you establish your model, especially if you have these energy management initiatives, energy reduction targets thrown down from the corporate, they will use that model to judge you versus the other facilities. So you want to know that you're judged the right way. Budget might be apportioned based on the results of this. So if your analysis says, I'm going to use 10% less gas coming next season, somebody in accounting might say, then you need 10% less amount of money to run the facility. Then the next year will be really hard to explain why you're 10% over the budget. So you want to make sure that the model is correct and that you understand the implications, sensitivity of the model. What if the model is slightly wrong, which way I'm going? So now we need to know, okay, we did the baseline, we have the model, we're happy, but before we call somebody and put a flag up and say, we have a model, we can now predict the future, we know everything, we may want to check it. Which is why I usually recommend collecting the data for 2 times your base period. Because you want to have, let's say, 1 year of the base period to build the model, and then you're going to use 2nd year of the historical data to check your model before you tell somebody that you know what the model is and that you know what the future looks like. So we know that this is the model. We just generated it. So let's populate the temperatures for the next year. Let's say we had another year in our back pocket. So this is the prediction of that model. You'll notice now timestamp is 2014, for example. We have predictions. We're all happy. We know how the model works. How we check it against consumed gas for that year. So we put consumed gas. Now we total them. Oops. We actually used more energy than we predicted. That's not a good thing. So, is it a model's error, or is it reality? We actually use more gas. Anything can happen. So if we, our energy team, have the logbook that says we did these steps, we implemented these changes, we all strongly believe we should have used less. I'm sure we used less. And we have not tested this model before. This is the first time we used it. We may want to go back and reevaluate our energy drivers just one more time. So we already know what the energy drivers were. We said outdoor weather, production levels. Those are the energy drivers. We were supposed to go and ask the process owners, is there anything else that can potentially affect your energy? No, we don't have anything. That's how we did. What if our material is stored outdoors, covered, exposed to snow drifts, and then we put them in the oven directly? I purposely did this far-fetched example. This is not the real-life example. Because there could be the littlest little detail that we skipped. Now with the snow drifts, I actually can go back and check what the snow drifts were for that year. Go back into my baseline model and check them even for 2013 because I have the data on some site. But what if that energy driver that we missed was a setting on some machine that we don't keep a log of? You just threw away your whole baseline period, and you have to do baseline again. That's why it's very important to catch energy drivers up front. Even if you have too many of them, it's better than not have enough. So now if we did this whole process again with 3 variables, you will notice that there is a B3 component to it. We follow the same steps. We get the same coefficients, this time modified. Look at our model now. Adjusted R-square 0.967, standard error 3,800. Model still looks good, right? Let's see. So now predicted for our original baseline, modified now for the snow accumulation for 3 parameters. We have predicted natural gas. For the post-retrofit in the second year, we have consumed gas, natural gas predicted. Much better. Now we have better results. Right? So we're in the right direction. Okay, so what did we do wrong? Right? We had a model that had a very good parameters. Everybody will tell you 0.95 is an excellent adjusted R-square. There is no reason to doubt your model. So we just jumped in and we said, this is the right model. We never even investigated anything past that. But this turned out to be an important mistake in our example. It turned our facility from the energy overconsumer to the energy saver. That can have huge implications if you're part of the large corporate chain. What if that result was used to compare us to the other planes? You would look really bad. So we want to make sure that these numbers, these models that you get, are as realistic as possible before we announce them. This is the second question that we'll get a lot. How do you know with these little adjustments here or there that now you're actually correct? It just happens to be that you're now a saver, so you pick that one. That's a fair question. And if you have to make a mistake on that side anyways for your future. Essentially, all your models are wrong. Some are useful. George Box is the famous statistician in the early 1900s in England. So he himself would always acknowledge that no model is actually 100% accurate. So let's compare the 2 models. Let's see where we at. On the right-hand side is the previous model, baseline. On the left hand is the modified baseline, the new example with 3 parameters. So adjusted R-square, 0.949, went to 967. So we went in the right direction. It's actually significant change. But also our standard error went from 4,800 to 3,800. Our intercept got better. Seems to be less of the load that we cannot explain by what we use. So no drastic changes, but some improvements. But how do we look at these improvements now? So adjusted R-square improved. Standard error improved by 20% of the original, 4,800 down to 3,800. So it means the model got tighter. It means the model thinks it's now closer to the reality. Intercept got smaller by almost 25%. So there's far less load that's left unexplainable by the model's parameters. So we moved in the right direction. We went from, 18,000, almost 10%, down to 14,000 cubic meters that we cannot explain. So that means that that variable that we added is actually statistically important. There's no other material changes in this. So that leads us to believe that, yeah, this is probably the good model. Which leads us to another example that we have in your workbook, a guideline when creating a model. All of that that we talked about can be summed up in this slide. Start with many drivers as you can possibly identify. Use even those that are not influential at the first blush, because at least you will have the data available to you for later analysis. So if you do 5 parameters and you end up with a p-value of 5 on 2 of them, you can always discard them out of the data set. You cannot easily add them always. Create a model, check the key parameters that we checked. Adjusted R-square, standard error, p-values, f-statistic, intercept. Remove the drivers which have p-value that's over whatever threshold, in this case 0.05. And repeat those steps over and over. Iterate the model until you're happy with the parameters and the output of the model. Once you're happy with the model, you got the best parameters you can, you're now satisfied, this is your model, do a reality check. Does the consumption drop with outdoor temperature? What happens with production output? Is it when I'm increasing production, my consumption prediction increases as well? Do a reality check. Does that make sense for me, for my process? Only then, when you're satisfied with those, go ahead and use the model for the future prediction. This cannot be overstated. Importance of this baseline is so big when you do energy management, it cannot be overstated easily. So you need a strong foundation. You need a baseline, no matter how you look at it. You need to know where you're starting from. You can use that baseline as a map for your energy efficiency future. You can have an idea what you want to do, where you want to do it, which equipment you should focus on. Instill a culture for other departments to use this map, to understand, guide, quantify the opportunities. And ultimately, energy management without this calibrated is the key baseline, is a house of cards. It's not whether it will fail, it's only when it's going to fail. So baseline is very, very important. Spend the time doing a proper baseline, and your energy management will be so much better later on. So it sounds very daunting. It sounds very difficult task. And now everybody's thinking, am I going to account for all the energy drivers? Am I going to do all that? But fundamentally, this is continuous improvement process. This is Kaizen. This is lean manufacturing. This is all the stuff that we are already very familiar with. If you're not sure about regression analysis, go talk to your quality assurance guy. I think that he can probably bore you to death with all the analysis that they do. They're familiar with all the statistical stuff. And you don't have to go elsewhere. You can just talk to them for 15 minutes. Buy them a coffee. Spend time to do this baseline. Look at this baseline as Kaizen calls this document reality step. So document what is your actual reality. That's your baseline. So you do that. When you do Kaizen event, and you say, how do we do today? How do we take this material from this place to that place? And you draw all these fish diagrams and all those things. That's your baseline in energy management. No different. So you already know how to do it. And once you do it, this is what will allow you to do. You will be able to predict the future energy consumption. You will identify potential savings and investments. You will verify the savings. So if somebody sells you energy efficient equipment and you want to maybe ask for a warranty on how much you'll actually save, you can verify them. And you can have verifiable record of your energy efficiency initiatives for your vendors, for your customers. Some customers nowadays will ask you, how do I know that you're actually energy efficient? If you have energy baseline model, you can show the progress. It's statistically valid. It's acceptable way of showing progress. So the process itself, again, to set up this energy model is very simple. Define the boundary, define the baseline time frame. Observe the energy use in that boundary and in that time frame. Prioritize what the energy drivers are, check them, build a baseline model, recheck the baseline model again, and then start using it for the future. This is no different when you look at it than actually managing the energy later on, because you'll follow these same steps. Observe energy use, identify improvements, execute the opportunities, verify the impact, act on it, and go back to observing. So when we had that continuous improvement below the management sponsorship, energy goals, energy team, we had that big box that says continuous improvement. This is what it is. Again, no different than your continuous improvement today. If you took your continuous improvement process that you have now for raw materials and you added line for energy, you would not be far off. You do not need a separate process for this. You can incorporate it. This is your typical continuous improvement. You didn't even notice when the slide changed. All it changed is just a generic description in the boxes. The process, the thought process, the setting up of the process is identical. One thing that I would like to bring to for the end of this session to the forefront is this importance of ACT. Because we had plan, do, check, act. And lots of people are like, well, do and act. It's sort of like the same thing. It's not. It's really not. Observe. Some people have OPDCA process rather than PDCA process. So first step is observe what your current status is. Plan. Based on what you observed, what are your objectives for the next little while? Do. Implement those objectives. So keep a logbook of these events so you know what you've done. So when the model is not right, you know at least, well, I think that all these steps should lead to something. So that's an important step to have. You have to have specific actions, specific events. This is no different than events in the Kaizen. Check. Study those results. So you made a change. Check whether that made actual change that you were hoping for, whether the reality matches what you expected. And then act. If it is the same, if now there is a better way of running your process, if there is a better way of managing the energy, implement those new standards of performance. So if you have 3 shifts and the shift C consistently is outperforming shifts A and B, find out what shift C does, make it standard operating procedure for all shifts. Without that, you will not have persistence of savings. That's the goal. And as a further proof of our involvement in this, for 2015, we are actually launching now a brand new program called Comprehensive Energy Management Program, which is available now, where our ESCs will act as your guides throughout the process to help you set up the energy management structure discussed before. And the energy management structure is quite simple. It is listed on the front page of your workbook, and it looks like this. You will see that two graphs combined. That's essentially what it is. So we need senior management sponsorship, energy team consolidation, long-term energy reduction goals, and then to set a cycle of continuous improvement. It's as simple as that. There's, of course, always some rules. Those rules will be explained to you if you're interested in this process by your individual ESC, or you can drop me a line and ask for more information. But this program is available now. So we will actually help you, not only guide you through the process, we will also give you implementation incentives for buying meters, data collection software, training, those kind of things. We will also help you implement any energy reduction initiatives identified through that program with some additional financial incentives. And we will work with, to the best of our abilities, with LDCs, NRCan, and all other partners to enable you to get as much money back as possible. So whoever is interested, please talk to your ESC or directly email me, and I will be able to answer any questions. But that's now available for your information.